Okay. Anyway, anyone have a question?
Yeah, I do have a question, Professor. So I would like to review some of the
For what
proof, like,
class?
Math 316, number 3.
Okay,
From the final review, I would like to review some of the proof, like question 17.
okay, just 1 second. Let me pull it up.
Okay, thank you, appreciate it.
Okay, number 17. So we're talking about finite groups. And we want to prove, so let G be a finite group of order n. Prove that if X is an element of G, then X to the D is the identity for some divisor D of n. So let me just point out, we already saw this in the case of congruences. So if G is, if you take the group of congruence classes mod n, but only the ones that are relatively prime to n, then the order of G is exactly phi of n. And we know that if you take any congruence class x plus nz, x plus nz to the d is 1. For some divisor d of, in this case, sorry, let's say we take this to be z mod mz. So the order is phi of m. So this is like the n for the order of the group. So 1 plus mz, z, this congruence class x plus mz to the power d, which is x to the d plus mz, is 1 plus mz for some divisor d of the order of the group, which is n. So we use this fact in number theory all the time. And I just want to see how I prove this. Right. So I proved this in the textbook. I proved what in the book is theorem 215. Which is Lagrange's theorem, which says that if G is a finite group and H is a subgroup of G, then the order of H divides the order of G. And what I'm asking you to prove in this problem is a special case of this, because suppose we take X in G. So the subgroup generated by X, which is what we call a cyclic subgroup, is the set of all powers X to the K. K 0 plus or minus 1 plus or minus 2 and so forth. All the powers of X certainly form a subgroup, because if you have X to the K times X to the L, that's X to the K plus L. So this is closed under multiplication. X to the 0 is the identity and so on. And if G has order n, then if you look at the sequence of elements, E, X, X squared, X cubed, up to X to the n, this is formally n plus 1 elements. But they can't all be different, because there are only n different elements in G. So they're not all distinct. So this means that there exist integers K and L between 0 and n, K strictly less than L, such that X to the K equals X to the L. Right? They can't all be different. Which means if you multiply X to the K equals X to the L by X to the minus K, here you have X to the 0, which is the identity. And here you have E to the X to the L minus K. And L minus K, this is some positive integer between 0 and n. So this means there exists a smallest positive integer d such that X to the d equals E. And so this cyclic subgroup, let me call this X with brackets around it. This is a subgroup of order D. So by Lagrange's theorem, the order of a subgroup divides the order of the group. D divides n. So if you are allowed to use Lagrange's theorem, then this is an immediate corollary. Okay. And you can see the proof of Lagrange's theorem in the text. Or I can do it now, but in any case, this is the idea of the proof of this problem. Any questions about this? Okay, what is your question?
Yes, so I would like to like continue like with proof. Like for example, let's say, what about 20?
Okay. So problem number 20 on the review is if P is a prime and P is congruent to 1 mod 4, prove -1 is a quadratic residue. That is -1 over P equals +1. So one way to do it is the following. Let G be a primitive root mod P. So every non-zero congruence class is a power of G mod P. And so this means that P minus 1 is the smallest positive integer. Such that G to the P minus 1 is congruent to 1 mod P. Now, P minus 1, so if P is congruent to 1 mod 4, that means P is an integer of the form 4K plus 1, which means P minus 1 is 4K, which means P minus 1 over 2 is 2K. And if we let, let's say, B be G to the P minus 1 over 2, what can we say? First of all, B is not congruent to 1 mod P, because the smallest power of G, that's 1 mod P, is P minus 1. And B squared is G to the P minus 1 over 2 squared, which is G to the P minus 1, which is congruent to 1 mod P. So what this means is B is a root of the equation x squared congruent to 1 mod P. Go see that x equals B, you get 1. But this only has 2 solutions, right? Because the integers mod P are a field, so a polynomial of degree 2 has at most 2 solutions. So the only solutions are x equal to 1 mod P or x equal to minus 1 mod P. These are 2 different solutions of this equation, and these are the only ones there are. So if B is a solution and B is not 1, then B is congruent to minus 1 mod P, right? And B, what is B? B is G to the P minus 1 over 2, which is G to the 2K, which is G to the K squared, which is minus 1 mod P. So if you let, I don't know, A be congruent to G to the K mod P, then A squared is minus 1 mod P. That is, I found the square root of minus 1 mod P. So minus 1 is a quadratic residue. It's a square mod P. So, I mean, there are many proofs. This is one proof.
That makes sense, Professor. Thank you. Professor, there is a student from Math 348 asking a question in the chat.
in the chat. Thank you. Okay, so if you can just wait a few minutes, let me finish the number theory and then I can go to the linear programming and game theory. Any other number theory questions?
Hi, Professor. Yes. So I was working some of the problems and I would like you to check what I did to see if what I did is correct. If not, like if you can go over.
Okay,
So give me, can you give me permission to share?
just 1 second. Okay, you should be able to share your screen now.
Okay, so this is question 32 from the review.
Mhm.
Give me a second. So this is like, if I think this is a following.
I don't see your,
Yes, so now it's gonna show up.
okay,
So I found the quadratic residue for 13 and number 31. So I did this according to what I found.
right.
So is this correct?
That is exactly correct.
Okay.
Right.
And then
There should be 6 quadratic residues and you found them, so that's fine.
okay. And then there's another question from the homework that I also did. So during the class, you found out the all prime breeze for which 5 is a quadratic residue, right? So in the homework, you asking for -5. So this is what I did for -5. Give me a second. Can you
Right,
see
so
it?
-1 is a quadratic residue. Mod P, if P is congruent to 1 mod 4. Yeah, that looks exactly correct.
Okay. And then my last question, this is, and I'm sorry. This is from the review too. So this is our proof, and this is 21B. Can I use the kind of proof here?
See, 21B, let me just see. So to prove Euclid's lemma. Well, so so what you really did is just restate Euclid's lemma, but you didn't prove it, right?
Okay, so can you go over that proof, please?
Sure. So this is number 21B. So let P divide AB. If P divides A, we're done. If P does not divide A, then the greatest common divisor of P and A is 1. And so there exist integers, X and Y, such that AX plus PY equals 1. So take this equation and multiply by B. You get ABX plus PBY equals B. But if P divides AB, that means AB is P times C for some integer C. So I can replace this by PC. I get PCX plus PBY equals B. But from this, I can factor out a P. It's P times CX plus BY. So P times this is B. So P divides B. So if P does not divide A, then P divides B.
Got it. Yeah. So this is like kind of how is it? Beso lemma, something like that, right?
What?
When you put like AX plus BY.
I'm sorry, I did not understand what you are asking.
I don't know how to pronounce the name, but it's okay, Professor. Thank you.
Okay. Okay. Any other number theory questions?
I don't know if Eddie has another question, but I'm done.
Someone had a question in the chat about the Math 156 final. There's a lot of, I've already started to grade them, and there's a lot of, I give a lot of partial credit. Okay. Any other number theory?
I'm good, Professor.
Okay.
I just wanted to ask, like, can you post the other